But then something shifted on November 4th, 2025, as the interstellar traveler, known as 3I Atlas, made its closest approach to our sun. It behaved in a completely unforeseen way. A development that has sent astronomers scrambling for answers. In fact, what they are now uncovering is forcing some scientists to confront questions they never imagined they would need to ask. Let me be clear, this isn't just another comet making a routine pass through our solar system. This is about an object that journeyed for billions of years through the vast, dark void between stars, an object that is defying all expectations. And the more data we gather, the more baffling this mystery becomes. Let me walk you through what's unfolding as we speak, because the events of the past few days have completely upended our understanding of this celestial visitor. As 3I Atlas neared perihelion, its point of closest encounter with our sun, something truly extraordinary took place. The comet's brightness didn't just gradually intensify as predicted. It erupted, surging at a rate double what had been previously observed. An acceleration that was twice as fast. Astronomers Chi-Chang Zhang of Lowell Observatory and Carl Battams from the U.S. Naval Research Laboratory documented this event in real time. And they were at a loss for an immediate explanation. Just pause and consider that for a moment. This object has journeyed through the depths of interstellar space for potentially billions of years. It has traversed environments so alien we can scarcely comprehend them. And now, upon nearing our star, it suddenly becomes far more active than any scientific model could have predicted. The question is why? And the spectrum analysis offered a startling clue. It turns out the light from the comet had become distinctly bluer than the spectrum of our own sun. This blue hue points to the presence of carbon molecules, specifically C2 and amidogen compounds, or NH2, which are telltale signs of active ice sublimation. But this is where the story takes a truly unsettling turn. Radio observations revealed that in the mere 2 weeks leading up to perihelion, 3I Atlas was shedding an incredible 5.7 times 10 to the 28th power water molecules every single second. That is a staggering 40 times more than it was losing only 1 month prior. 40 times the amount of water gushing out into the vacuum of space. An outflow one scientist described as being like a fire hose on full blast. Now, you might be thinking, this sounds like typical comet behavior. After all, comets approach the sun, their ices vaporize, and they brighten. It's standard physics. Except, in this case, it's not. 3I Atlas isn't playing by the established rules. The rate of its transformation is off. The timing of its outburst is wrong, and its behavior simply doesn't align with what we've observed from comets originating in our own solar system. This is where the plot thickens. Thanks to our space-based telescopes, instruments aboard SOHO, Stereo A, and the new GOES-19 satellite, all outfitted with coronagraphs designed to watch objects near the sun, managed to capture images of 3I Atlas during this crucial time frame. And their findings were highly unusual. In the images, the comet was visible as a faint but clearly elongated smudge of light. But the truly strange part, there was no visible dust tail. Absolutely none. There was only this stretched out glow, completely lacking the signature dust trail that comets almost always leave behind. So, what could this possibly mean? Well, one leading hypothesis suggests that initially, carbon dioxide gas was venting from the comet at a distance of roughly 3 astronomical units. This outgassing of carbon dioxide would have had a cooling effect on the nucleus's surface, essentially acting like a protective shield that kept the water ice from turning directly into gas. But then, as we know, something changed. That protective layer was stripped away, and when it vanished, the water ice beneath it was abruptly exposed to the full force of solar radiation. The consequence? a cataclysmic surge in brightness and activity. However, there's an alternative theory to consider. And this is the part of the story that makes some scientists uneasy. The very makeup of A3, Atlas's core, could be unlike anything humanity has ever encountered. Keep in mind, this celestial visitor did not originate within our own solar system. It was born in orbit around another star, within a unique stellar nursery under entirely different chemical circumstances. What if its internal architecture bears no resemblance to the comets we know? What if something lies dormant within its core that defies our current understanding? The James Webb Space Telescope has turned its powerful gaze upon A3 Atlas, and its findings have only deepened the enigma. Webb's near-infrared spectrograph data indicates that this comet has been profoundly altered by billions of years of relentless cosmic ray bombardment. And we're not just talking about any radiation. We're referring to galactic cosmic rays. These are high-energy particles that saturate the void of interstellar space, having pelted the comet's surface ceaselessly for ages. Based on research spearheaded by Roma Maggiolo of the Royal Belgian Institute for Space Aeronomy, it appears these cosmic rays have radically changed the physical and chemical composition of A3 Atlas. Computer models indicate that these rays have bored approximately 50 to 65 feet into the comet's surface, forging what scientists now term a deep irradiated crust. This outer layer bears little resemblance to the untouched primordial material from the comet's native star system. It has been baked by radiation for such an immense span of time that it has transformed into something completely new. And this is where the entire paradigm shifts. Researchers had hoped that interstellar objects such as A3 Atlas would offer a clear window into other star systems, allowing us to analyze these travelers and understand the conditions around faraway suns. However, if Maggiolo's research is correct, what we're actually observing is not an immaculate sample from another solar system. Instead, it's a heavily altered radiation process shell, fundamentally reshaped by its long voyage through the interstellar medium. Maggiolo made a statement that should give every one of us a moment of pause. He stated that A3 Atlas is now more a product of its interstellar travels than its place of origin, at least externally. This, of course, begs an obvious question. What lies beneath that radiation-hardened crust? What is concealed in the heart of this object that could still be untouched material from its home system? And now for a detail that most people are unaware of. Professor Avi Loeb, the former head of Harvard's astronomy department, has officially demanded that NASA make all of its scientific data on A3 Atlas available to the public. Why would he make such a request? What does he suspect is hidden within the data that NASA has yet to share? The conduct of A3 Atlas following its closest approach to the Sun is now under intense scientific observation. Researchers openly concede they cannot predict what will happen next. Will its luminosity continue to climb, or will it abruptly dim? In their observations, Jong and Badams remarked that the comet's evolution post-perihelion could prove to be every bit as strange as the outburst that came before it, perhaps even stranger. And it is precisely that uncertainty which makes this moment in time so pivotal. We are witnessing, in real time, an object from outside our solar system behaving in ways we cannot completely comprehend. At its closest approach to the Sun, what we call perihelion, Comet 3 Atlas, shown with a visual magnitude of roughly 9. That's bright enough to be spotted with small amateur telescopes. Assuming you knew exactly where to look, but here's the catch. From our vantage point, it was positioned so incredibly close to the Sun in the sky that observing it from Earth's surface was nearly impossible during that crucial period. We had to rely on specialized space-based coronagraphs to see what was truly going on. And what they revealed was an object that looked nothing like a conventional comet. The images captured an elongated, glowing form, but it was strikingly absent of the expected classic dust tail. Instead, what we were witnessing appeared to be composed primarily of gas emissions, particularly a distinct hydroxyl glow. This signature, indicative of water vapor escaping from the comet, was successfully detected by NASA's Swift Ultraviolet and Optical Telescope. But the absence of any visible dust is highly unusual. Comets are supposed to produce dust. It's what forms their magnificent tails. So where could the dust from Comet 3 Atlas be? One possibility is that its composition is fundamentally rich in ice, with very little solid material to generate dust. But that explanation doesn't fully account for its explosive brightening. This brings us to another possibility, and this is where things get uncomfortable for some researchers. The idea that this object's internal structure is unlike anything we've ever classified. Now, let's pivot. Let's discuss what the James Webb Space Telescope uncovered. Because this is where the narrative veers into territory that challenges our fundamental assumptions about interstellar objects. Webb had observed Comet 3 Atlas back in August, prior to its perihelion passage. Its near-infrared spectrograph instrument analyzed the light radiating from the comet, examining the specific wavelengths that act as fingerprints for the molecules present. The data confirmed something that previous observations had suggested. This comet is exceptionally rich in carbon dioxide, unusually so. But more importantly, Webb's analysis showed that the outer layers of this object have been fundamentally transformed by cosmic radiation. Let's explore what that implies. Within our own solar system, we exist inside a protective bubble called the heliosphere, created by the solar wind that constantly streams from our sun. This heliosphere serves as a shield, protecting us from the majority of galactic cosmic rays. These are high-energy particles originating from supernova explosions and other violent cosmic events. In the void of interstellar space, however, no such protection exists. Objects that drift between the stars are exposed to the full, unmitigated intensity of this cosmic ray bombardment for millions or even billions of years. Computer models developed by Maggiolo and his team, which were adapted from earlier studies of our local comets, simulated precisely what occurs when ice and rock are exposed to cosmic rays over extended periods. The simulation demonstrated that after approximately 1 billion years of radiation exposure, the transformation is complete. The outer layers are fundamentally altered. Carbon monoxide gets converted into carbon dioxide. The crystalline structure of the ice is reconfigured. Chemical bonds are broken and then reformed in entirely new patterns. The result is a crust that penetrates approximately 50 to 65 feet into the comet's interior. This forms a shell of radiation process material that no longer reflects the original composition from the comet's home system. And here's the unsettling part. We have no idea how deep this crust truly goes. It's a mystery whether the sun's heat will strip away its outer layer to show us the untouched material inside, or if the entire object has been fundamentally altered all the way to its core. Maggi made it clear that scientists must factor in these cosmic aging processes when they analyze 3A Atlas. You can't just presume you're observing a fresh sample from another star system. You're looking at something that has been weathered by the harsh realities of deep space. But he also offered a significant ray of hope. He noted that 3A Atlas remains incredibly compelling despite this issue. Because if we can decipher how the radiation crust was formed and compare data from before and after its closest solar pass, we might just be able to glimpse its original composition. That is precisely what scientists are waiting for. The comet has rounded the sun and is now heading away from it. And in November and December of 2025, it will swing back into view from Earth as it continues its journey out of our solar system. This is our moment. This is when we might finally see if the solar furnace has burned away enough of that radiation-blasted crust to reveal what lies beneath. But there's another twist to this tale. Something that doesn't quite fit the textbook definition of a comet. Susanne Falsner, a professor at Forschungszentrum Jülich in Germany, has introduced a radical new theory about interstellar objects like 3A Atlas, suggesting they aren't merely cosmic debris. They might, in fact, be the seeds of planets. Her computer models indicate that young stars, enveloped in their planet-forming disks of gas and dust, could capture millions of these interstellar travelers as they drift through the galaxy. And once captured in that gravitational dance, these objects, already hundreds of meters across, could become the very nucleus around which new planets begin to grow. This potentially solves a persistent problem in the field of planetary science. We understand that planets form through accretion, with small particles clumping together into progressively larger bodies. But our understanding has a major gap. Computer simulations consistently predict that once objects grow to about a meter in size, the chaotic swirl of a protoplanetary disk should cause them to shatter on impact, not merge. So, how do we get from meter-sized rocks to planet-sized worlds? Falsner's answer is brilliantly simple. You don't begin with meter-sized rocks. You start with interstellar objects that are already large enough to gravitationally pull in material and jumpstart the entire planet-building process. Interstellar space itself could be delivering ready-made seeds for the next generation of planets. And here's the real kicker. Her models propose this mechanism works exceptionally well around massive stars. Stars far larger than our Sun, which would explain why gas giants like Jupiter are so much more common around these larger stars. This is true, even though the planet-forming disks around those stars last only about 2 million years, far too short a time for traditional formation theories to play out. So, when you look at 3A, Atlas, you are not just seeing a comet. You are potentially looking at the kind of object that could have become a planet, had it been snagged by a young star's gravity billions of years ago. You're observing a building block for a world that never was. And that single thought changes the entire context of what we're witnessing. But let's circle back to what's happening now. Because the most captivating part of this saga isn't just what we have already discovered. The real mystery lies in what remains unknown. And the flight path of 3I Atlas is anything but ordinary. It's blazing through space at over 130,000 miles per hour relative to our solar system, following a trajectory that observers have noted is remarkably flat and direct. This is a far cry from the chaotic, arcing path we'd anticipate from an object that was formed within our own solar system, one that's been tugged and pulled by planetary gravity for eons. Instead, this is a trajectory that practically shouts, "I'm not from around here, I'm just a tourist passing through." Some estimates place the age of 3I Atlas between 7 and 12 billion years old, which would make it roughly 3 billion years more ancient than our entire solar system. Let that sink in for a moment. This celestial object was around before our sun even began to shine, before the Earth itself was formed, before any of the planets we recognize even existed. It has been journeying through the cosmos since a time when our Milky Way galaxy was a vastly different place. Imagine the cosmic sights this traveler has witnessed. What strange environments has it traversed? What nascent star systems did it silently drift past in the void? Never quite close enough to be captured, but near enough to be bathed in their radiation, their stellar winds, and their unique cosmic neighborhoods. We are certain it originated somewhere on the galactic frontier, possibly from the far-flung reaches of the early Milky Way. But its exact birthplace remains a complete mystery. We have no idea what star it once called home, or what fate befell that star. We can't say if it was violently ejected from a young planetary system by the gravitational dance of forming gas giants, or if it simply coalesced in the cold, dark expanse between stars, destined to wander for eternity. What we can say for certain is that right now, at this very second, 3I Atlas is speeding away from our sun, plunging back into the interstellar darkness. And our window to collect crucial data is rapidly closing before it vanishes forever. Once it's gone for good. This is truly a once-in-a-lifetime opportunity for science. And this urgency brings us directly to Avi Loeb's recent plea to NASA. Professor Loeb has been a prominent advocate for complete transparency regarding these interstellar visitors. He was a leading voice demanding a thorough scientific investigation of Oumuamua, our very first confirmed interstellar guest, which zipped through our solar system back in 2017. Loeb's position then, as it is now, is that when we are faced with extraordinary data, we must not be too quick to dismiss extraordinary possibilities. He argued that Oumuamua's peculiar, elongated shape and its mysterious acceleration as it departed our solar system, coupled with its lack of a typical cometary tail, were all anomalies that warranted deep investigation, not hasty, conventional explanations. Now, in the case of 3I Atlas, Loeb is urging NASA to release all of its scientific findings to the wider research community and the general public. His reasoning is crystal clear. This object holds immense scientific importance. After all, it is only the third confirmed interstellar visitor we have ever managed to detect. The information gathered by NASA's sophisticated instruments, including the Swift telescope, SOHO, Stereo, and GOES 19, represents our single best opportunity to truly understand the nature of these interstellar objects. That information shouldn't be locked away. It needs to be made available for independent analysis by scientists all over the globe. But lurking just beneath the surface of Loeb's request is a tantalizing, unspoken question. What, precisely, does that data contain? What has NASA seen that they haven't yet shared with the world? Are there observations, spectral readings, or behavioral quirks that defy easy explanation in press releases and initial reports? When it comes to interpreting 3I Atlas, the scientific community finds itself at a crossroads. One camp of researchers is content with the theory that it's merely a comet with a peculiar composition, modified by eons of cosmic radiation and behaving in ways we've never witnessed, simply because we've never had a front row seat to an interstellar visitor like this. They highlight the presence of carbon dioxide, the signature of water vapor, all the molecular evidence that screams comet. A strange one, to be sure, but a comet nonetheless. Yet, other scientists aren't so certain. They focus on the anomalies, the sudden, dramatic brightening that defies our predictive models, the curious absence of a significant dust tail, and its remarkably precise trajectory. They raise the unsettling possibility that its very core is fundamentally different from anything native to our cosmic neighborhood. Asking quietly in research papers and at conferences, what other explanation fits these observations? No one is willing to state the alternative explicitly. No credible scientist wants to be the one who leaps to an extraordinary conclusion without extraordinary evidence. But the questions linger. They hang in the intellectual ether, much like the comet's own ethereal coma. What if 3I Atlas isn't a purely natural phenomenon? What if some aspect of its makeup, its structure, or its activity hints that it's something more than a simple ball of ice and rock on a billion-year journey through the void? And this is precisely what makes that question so profoundly unsettling. We lack the scientific framework to even begin to answer it. Our entire scientific paradigm for comets, asteroids, and interstellar objects is built upon a foundation of known natural formation processes. We analyze a spectrum, detect carbon dioxide in water, and our training tells us to classify it as a comet. We observe an elongated shape and theorize it's a fragment from a planetary collision. We map a trajectory and we calculate the gravitational tugs from distant star systems. But what happens if the very signatures we've been trained to recognize could point to more than one conclusion? What if some of these observations are ambiguous, fitting the profile of both a natural object and one of artificial origin? How could we possibly distinguish between the two? This isn't about proclaiming that 3I Atlas is anything other than what it seems. It is about candidly admitting that our entire catalog of interstellar visitors consists of just 3 objects: Oumuamua, Borisov, and now 3I, Atlas. A mere 3 data points from the billions, or perhaps trillions, of objects estimated to be roaming our galaxy. We are attempting to define an entire class of cosmic phenomena based on a trio of examples. That hardly qualifies as robust science. At best, it's preliminary observation. And it's crucial to note that every single one of these 3 visitors has brought with it a profound surprise. Oumuamua displayed an acceleration that outgassing alone couldn't account for. Borisov, by contrast, seemed relatively conventional, though it carried chemical signatures from a completely different stellar neighborhood. And now, we have 3I, Atlas, which is flaring up with explosive brightness, shedding water at an astonishing rate, and fundamentally challenging our models of how a long, irradiated comet is supposed to act. Perhaps the simplest answer is that all 3 are merely natural objects, each with its own unique and unusual characteristics. It could be that the universe is simply far more varied and complex than our limited experience has led us to believe, and that each new interstellar guest will expand our knowledge of the diverse environments and formation processes that exist across the galaxy. That is the most straightforward explanation, and in all likelihood, it is the correct one. However, the sheer violence of 3I, Atlas's outburst, and its very specific timing, leaves the door open to deeper questions. But the timing, happening exactly at its closest approach to the Sun, is a detail that just won't let go of some researchers. You see, there's a fine line between something being merely unusual yet explainable and being so strange that it points to a factor we've completely overlooked. So, let's look ahead, because the saga of 3I Atlas is by no means finished. As the comet begins its journey away from the Sun, it's expected to stay within our view throughout November and December. And you can bet that astronomers globally are locking their telescopes onto its path, diligently gathering spectroscopic data, charting its brightness, and monitoring every subtle shift in its level of activity. The one question on everyone's mind is straightforward. Will its activity finally subside as it retreats from the Sun's intense heat? Or could something else be on the horizon? Jiang and Batums were specific, noting that the comet's evolution after perihelion could be just as peculiar as its initial flare-up. But what exactly did they imply? What are they anticipating? Or, to put a finer point on it, what potential outcome has them so concerned? Well, one possibility is that the comet simply behaves, fading away just as we'd expect. As the Sun's heat lessens, the outgassing process slows, its brightness diminishes, and 3I Atlas dwindles into a faint point of light, eventually vanishing back into the cosmic darkness. That would be the textbook case. But there's another scenario. What if the activity persists, or even intensifies? If some hidden cache of material lies deep within its nucleus, a volatile substance now uncovered by the erosion of its outer crust, it might keep spewing gas even as it distances itself from the Sun. Such an event would be a clear signal that its internal makeup is drastically different from what we see on the surface. Then there's the third possibility, the one that scientists are hesitant to even whisper. What if its behavior shifts in a manner that solar heating alone simply cannot account for? What if a pattern emerges in its activity, one that points not to external forces, but to something happening deep inside the comet itself? What could that possibly imply? Interestingly, the 2 Mars rovers, Curiosity and Perseverance, were actually granted a unique opportunity to watch 3I Atlas from their exclusive viewpoint on the Martian surface. Their observations offered a completely different perspective, an angle that could potentially unveil details completely hidden from our view here on Earth. The full dataset from those Martian observations is still under wraps. So, what did they witness? Now, here's a detail that often goes unnoticed. This comet ventured so close to the Sun that the solar wind that relentless stream of charged particles blasting from our star. They would have slammed directly into its coma, the hazy envelope of gas and dust around its core. That kind of cosmic collision creates observable effects, like plasma instabilities, warped magnetic fields, and accelerated particles. And these phenomena can reveal secrets about the comet's composition and structure that simple light analysis could never show us. Enter NASA's STEREO mission, a project specifically engineered to monitor the sun and its far-reaching influence on the space around it, which actually captured images that show 3I Atlas caught in a dance with the solar wind. These images unveiled distinct structures within the coma, lopsided patterns in its gas distribution, and other signs that point to some incredibly complex dynamics at work. However, deciphering these patterns isn't just a matter of cometary physics. It demands expertise in plasma physics, magnetohydrodynamics, and the turbulent, chaotic environment so close to our star. This is precisely why Loeb's appeal for total data transparency is so critical. Because the more expert eyes we can get on this data, and the more diverse perspectives we can apply, the greater our chances are of truly understanding what is going on out there. Perhaps one team of researchers will spot a crucial detail that another team has overlooked. It's possible an independent analysis could uncover a hidden pattern, completely reshaping our understanding. This is how science thrives, through openness, shared data, and subjecting strange observations to intense scrutiny instead of writing them off too quickly. And make no mistake, 3I Atlas is more than unusual enough to warrant that exact level of deep investigation. Now, let's pivot to a topic that's been buzzing across online forums and among amateur astronomers. Many have pointed out that the timing of this comet's flare-up, happening almost perfectly at its closest approach to the sun, feels a little too convenient. After all, natural phenomena are typically chaotic and unpredictable, marked by gradual shifts, not sharp, sudden changes. So, why did this explosive brightening happen at that precise moment? The conventional scientific explanation points to a threshold effect. As the comet absorbed more solar heat, it eventually hit a tipping point where the rate of sublimation skyrocketed. Imagine a protective layer of carbon dioxide ice vaporizing at just the right moment, exposing the vast water ice reserves beneath to the sun, all at once, triggering that massive surge in brightness. That's certainly a plausible theory, and it aligns with the laws of physics as we know them. But there is another, more provocative interpretation that many find deeply compelling. What if this object was engineered to power on at a predetermined distance from a star? What if the outburst wasn't a passive reaction to heat, but an active, internal process set in motion by its close pass with our sun? Now, before you label that as pure science fiction, think about this. We ourselves have sent probes to other worlds that are designed to activate at specific times or in specific environments. We've engineered satellites that lie dormant until they detect solar radiation hitting a certain threshold. The idea of a system triggered by a specific threshold isn't some exotic concept, it's fundamental engineering. So, the real question isn't whether such a technology is possible. It's whether there's any shred of evidence to suggest 3I Atlas is anything but natural. And the truthful answer is, we simply don't have enough data to definitively rule any possibility out. Another factor that makes 3I Atlas so fascinating is its sheer mass. Initial estimates place its mass at roughly 33 billion tons, which is absolutely colossal for a comet. To put that in perspective, most comets from our own solar system are significantly smaller. The famous Halley's Comet, for instance, has a nucleus estimated at around 22 billion tons. This means 3I Atlas is substantially more massive than one of the most celebrated comets ever recorded. Of course, immense mass by itself isn't a smoking gun. there are plenty of large objects roaming our solar system. But when you pair that mass with its other oddities, the incredible velocity, the explosive outgassing, its peculiar path, it becomes another compelling piece in a growing puzzle that makes this object so unique. And that brings us to its velocity. A speed of 130,000 miles per hour might not seem exceptional on a cosmic scale, but it signifies a very specific state of energy. This object is traveling with enough force to not only escape our solar system, but to journey between star systems for billions of years. It has been wandering through the void for so long that its home star might have ceased to exist long ago. That star could have run its course, ballooning into a red giant, casting off its outer layers, and finally collapsing into the stellar remnant of a white dwarf. And all this time, 3I, Atlas was journeying through the immense void of space. Just imagine that voyage, spanning between 7 and 12 billion years. If those age estimations hold true, this celestial object has been traveling since before complex life even began to emerge on our planet. It has traversed regions of the cosmos that we can only theorize about, and has survived encounters with an unknown number of stellar systems, weathering gravitational tugs from colossal objects and bathing in radiation from sources we haven't even identified. And yet, it emerged from all of that completely intact, still a coherent body, still a distinct object rather than a scattered cloud of cosmic dust. That alone is an absolutely remarkable feat of survival. Statistically, the survival rate for any object traversing interstellar space for billions of years should be incredibly low due to collisions with other bodies, gravitational forces that could tear it apart, and radiation damage leading to catastrophic structural failure. All of these are constant threats. And yet, here is 3I, Atlas, seemingly whole and behaving in ways that suggest it is held together exceptionally well. Despite its ancient origins, the irradiated crust detected by the Webb telescope could, in fact, be a key part of the explanation. This 50 to 65 foot thick layer of radiation-hardened material may be acting as a form of protective armor, shielding its core from additional harm, and preserving its structural integrity. It's effectively a shell, forged over billions of years by relentless cosmic ray bombardment, making it harder and far more resilient than the pristine ice that lies beneath. In a way, the journey itself is what fortified 3I, Atlas, making it more durable. But this is where things get particularly fascinating when you look at it from an engineering standpoint. Imagine you were tasked with designing a probe meant to travel between star systems. A probe built to survive the unforgiving environment of interstellar space for billions of years. How would you build it? You would absolutely need shielding from radiation. You'd require structural integrity capable of withstanding constant micrometeorite impacts. You would also need a design that could endure extreme fluctuations in temperature. And you would likely want it to be almost entirely passive, not relying on active systems for the vast majority of its long voyage, activating only when it encountered very specific conditions. An irradiated crust, like the one we see, would fulfill many of those design requirements. It would shield the interior. It would provide immense structural strength, and it would be formed naturally by the very environment it's traveling through, requiring zero active maintenance. Now, if something were housed underneath that crust, something designed to remain dormant until triggered by the proximity of a star, that crust would be the perfect way to keep it safe. Let me be clear. I'm not definitively saying that's what 3I, Atlas is. What I am saying is that when you examine the characteristics we've observed its immense age, its mass, that protective crust, and its threshold-triggered activity, you are looking at a set of properties that are also remarkably consistent with a deliberately designed object meant for interstellar travel. This, of course, doesn't prove anything. It simply underscores the need for us to be exceptionally thorough in our analysis. This is precisely why the scientific method is so crucial. You don't begin with a conclusion. You meticulously gather data, you rigorously test hypotheses, and you actively search for ways to distinguish between competing, viable explanations. At this moment, what we need is more data. The observations we'll be collecting over the next several weeks are going to be absolutely critical. If 3I Atlas begins to fade in a predictable manner, if its behavior perfectly aligns with our refined models of irradiated comets reacting to solar heating, then we will have a solid, natural explanation for everything observed, and the anomalies will be chalked up to an unusual, yet perfectly understandable composition and cosmic history. However, if its behavior consistently strays from what we've predicted, if we observe patterns of activity that don't align with its proximity to the Sun, and if spectroscopic analysis reveals a composition or structure that upends our fundamental understanding of natural comet formation, then we are obligated to expand our field of hypotheses. We will have to consider possibilities that currently seem far-fetched. And that makes many scientists uneasy. Because once you begin entertaining theories that exist outside the conventional framework, you invite criticism, accusations of wild speculation, and the risk of being labeled as fringe or sensationalist. But that professional unease should never stop us from following the data wherever it may lead. Avi Loeb has been especially vocal about this. He has argued time and again that the stigma around discussing non-natural origins for unusual objects is, in itself, unscientific. The very nature of science is to be impartial about the final answer. You formulate hypotheses, you test them against the evidence, and you follow where the results take you. If an artificial origin hypothesis can be tested and potentially disproven, then it stands as a valid scientific theory, no matter how uncomfortable it might make some people. The primary challenge is identifying what specific observations would allow us to truly distinguish between natural and artificial origins. What exactly would we expect to see that's different? What specific measurements? What telltale patterns? What definitive signatures would be the clincher? With a natural comet, we would anticipate its activity to correlate perfectly with solar heating. We would expect its composition to fall within the known ranges for ices and rocks that form in protoplanetary disks. We would expect any structural variations to be completely random, reflecting the chaotic processes of accretion. We would expect its flight path to show minor deviations from outgassing that precisely match the direction and power of any observable jets. For an object that was designed, however, we might anticipate precise, threshold-based behaviors, activity that switches on or off under specific conditions rather than evolving gradually. We might look for unusual symmetries in its structure or composition. We might anticipate trajectory corrections that simply can't be explained by passive outgassing alone. We might even detect radio emissions at frequencies suggesting intelligent modulation, not natural plasma processes. Have we even looked for these things? Have we actually run the tests that would enable us to distinguish between these radically different possibilities? That is precisely what Loeb is asking NASA to provide the data for. Let the entire scientific community examine every piece of it. Let independent researchers search for patterns. Let the analysis be as exhaustive and comprehensive as humanly possible. Because here is the undeniable reality. We are living in a moment of profound cosmic significance. For the first time in all of human history, we have the technology to detect, track, and analyze objects from entirely different star systems. We can aim our most advanced telescopes at these interstellar visitors and gather data that would have been pure science fiction even 20 years ago. The James Webb Space Telescope, launched just a few years ago, is giving us insights into the makeup and structure of objects at a resolution that is simply unprecedented. Our network of space-based observatories gives us continuous monitoring that ground telescopes by themselves could never achieve. This is the golden age of interstellar object research. But it is also an incredibly brief window of opportunity. These visitors are fleeting. 3I Atlas, will be gone in a matter of months, receding back into the immense void between the stars. We might not witness another interstellar guest for years, or even decades, making each one an invaluable opportunity. Each represents a chance for discovery that we simply cannot afford to miss, which is precisely why its explosive brightening is so critical. It's why the absent dust tail is so significant, why the radiation crust is a crucial clue, and why every anomaly, every unexpected behavior, and every deviation from our established models demands our most serious attention. Because we are not merely studying a comet, we are gathering data that could fundamentally reshape our entire understanding of what exists in interstellar space. Just imagine the implications if the space between stars is actually filled with objects like 3I, Atlas, billions upon billions of them, drifting silently between suns, carrying the chemical fingerprints of distant stellar systems, perhaps even transporting the very building blocks of planets yet to be born. The galaxy would transform into a vast ocean of potential, a reservoir of raw materials in constant, dynamic motion, perpetually redistributing itself across the unfathomable expanse of light years. But now consider the implications if even a small fraction of those objects are something else entirely, if among the countless natural comets and asteroids wandering the darkness, there are also artifacts, technological probes, or constructs dispatched by civilizations that thrived millions or billions of years ago. What would that mean for our comprehension of intelligence in the universe? What would it reveal about our own place in the grand cosmic narrative? We have spent decades searching for radio signals from the stars. We've looked for laser pulses and for engineered megastructures around distant suns, for any definitive sign that we are not alone in this vast cosmos. But perhaps we've been searching in the wrong places. Maybe the evidence isn't light years away among the stars. Perhaps it's right here, passing through our own solar system, disguised as natural objects, because that is exactly what they would be made of. Interstellar probes wouldn't look like starships from science fiction. They would appear as rocks, as ice, as comets. They would be designed to blend in, and the only way we could ever tell the difference is through careful, meticulous analysis of their behavior and composition. This brings us full circle, back to the data, and back to the crucial need for transparency in science. It brings us back to the fundamental question of whether we are investigating these objects with the thoroughness they truly demand. The next several weeks will be incredibly revealing, as 3I Atlas moves away from the sun, and as we continue to monitor its brightness, its spectrum, and its trajectory, we will gather more pieces of this extraordinary puzzle. It's possible those pieces will fit together to form a clear picture of a highly unusual, but completely natural comet. Maybe they will reveal patterns that challenge our current understanding and force us to expand our theories. Or perhaps, just perhaps, they will show us something we never expected. Something that makes us question our deepest assumptions about what is possible, about what truly exists out there in the darkness, and about whether we are as alone as we have always presumed. One thing is certain: we are watching, right now, at this very moment. Telescopes across the globe and in space are fixed upon 3I Atlas. Scientists are analyzing its spectra, calculating its trajectory, and modeling its internal structures with intense focus. Around the globe, amateur astronomers are sharing their observations, comparing notes, and joining a worldwide effort to understand this cosmic visitor as the data continues to pour in. The picture is gradually coming into focus, and no matter what we ultimately discover, whatever the answer proves to be, it will fundamentally change how we perceive the universe. Because every interstellar object offers us a brand new lesson. Each messenger from the void brings with it knowledge we could never acquire otherwise. Every single anomaly is a chance to refine our theories, to challenge our assumptions, and to push the very boundaries of what we know. This object Atlas originated somewhere far from here. It journeyed for billions of years to finally reach us, surviving conditions we can barely fathom. And now, for one fleeting moment in cosmic history, it is here, close enough for us to scrutinize, close enough for us to learn from. It is performing in ways we never anticipated, behaving in a manner that challenges our scientific models, and revealing properties that force us to think more deeply about what interstellar objects truly are. The question is not whether this atlas is peculiar. It most certainly is. The real question is what that peculiarity means. Is it the strangeness of a natural cosmos that is more diverse and complex than we've ever imagined? Or is it the strangeness of something else entirely? Something that prompts us to reconsider our most fundamental assumptions about our place within the galaxy. Time will reveal the truth. The data will tell the story. And that is precisely why we need all of it. It's why transparency is paramount. It's why Loeb's request to NASA holds such importance, regardless of the final outcome. Because when it comes down to it, this is about far more than a single object passing through our solar system. This is about our very approach to the unknown. It's about whether we possess the courage to follow the evidence, wherever it may lead, even if it guides us to uncomfortable conclusions. It's about our willingness to ask the difficult questions and accept answers that may be uncertain. This atlas is still out there, speeding away from us at over 100,000 miles per hour, carrying its secrets back into the immense darkness. But for now, during these precious few weeks, while it remains in view, we have an opportunity to learn, to observe, to question, to wonder, and maybe, just maybe, to discover something that changes absolutely everything. The interstellar visitor has come. It has put on its unexpected show, and it is now making its exit. What it leaves in its wake are questions, profound questions. Questions that demand answers. The universe is communicating with us through these objects. Are we paying close enough attention to hear what it is saying? Close enough to truly understand its message?